Now that we've discussed what makes an acid a weak acid and what makes it a strong acid, let's talk a little bit about why that happens. Okay, why is a strong acid and why is a weak acid a weak acid? If you think about it, what makes a strong acid is that the hydrogen ion or the hydrogen atom that's on that acid is able to come off pretty easily. And it's kind of funny because you think, well, it's a strong acid, that hydrogen should be held there strongly. A strong acid, remember, is one that contains that whatever the concentration of the acid is, that's what the hydrogen ion concentration is. Which means in a strong acid, the hydrogen is held on very weakly. Okay, whereas in a weak acid, that acidic hydrogen is held on fairly strongly. It doesn't really come off very easily to create H+ on the product side. So in a strong acid, the hydrogen is held on weakly and water can easily pull it off of there. Whereas in a weak acid, that hydrogen is held on stronger and therefore does not create very many hydrogen ions. Okay, another way you can think about it is think about it in terms of, remember, if the acid is strong, its conjugate base is weak. Okay, whereas with a weak acid, its conjugate base is strong. And when we say strong, we mean that it's stable. So a weak acid has a strong conjugate base. Okay, and we're going to talk about that a little bit today. Because one of the types of acids that you see pretty commonly on the AP exam, and this is more organic chemistry, but it does appear on the exam quite a bit, is an acid called a carboxylic acid. Okay, and you'll see that a carboxylic acid, in the past we always learned if it starts with a hydrogen, it's an acid. Okay, but a carboxylic acid is one that many times they write the way that it looks. So for example, propanoic acid right here, a lot of times they write it as CH3, which is that right there, and then they write CH2, that right there, and then the last part COOH. Okay, anytime you see COOH at the end, you know that that is an acid, and that hydrogen right there is the acidic hydrogen. So when you put that in water, certainly that is a weak acid. When you put it in water, you're going to get the equilibrium arrow. This hydrogen is going to break off, so you're going to get H+, and then you're going to be left with CH3, CH2, COO-. Okay? And again, because it's a weak acid, that hydrogen is actually held on fairly strongly. Okay? But if it were a strong acid, then again, like I just discussed, that hydrogen isn't held on very strongly. It easily comes off. Okay, so let's kind of look at some of these carboxylic acids. So we've got propanoic acid that has 3 carbons. Ethanoic acid, a more common name for that is actually acetic acid, but using the organic nomenclature, they call it ethanoic acid. And then there's methanoic acid. So notice you go from 3 carbons to 2 carbons to just the 1 carbon. Okay, even though those are all weak acids, which of the 3 is the strongest? Remember in our previous video we learned about pKa. The smaller the pKa, the larger the Ka value. So this one has the larger Ka. Okay, this one has the smaller Ka value, and so therefore the larger the Ka, the stronger the acid. Okay, and this one therefore is the weaker acid. Now, why does that happen? And again, sometimes they ask you a question about this. Well, why? Why is methanoic acid a stronger acid than ethanoic or propanoic? Okay, and the reasoning that you're going to use is you're going to say because the conjugate base of methanoic acid, which would be this hydrogen is going to break off, so you're going to be left with just the H, so you're going to be left with HCOO-. That's the conjugate base of methanoic acid. Because that's a stronger acid, because that's a stronger acid, it's a weaker conjugate base. And when it's weaker, it means it's less likely to reform the acid. And so the term that they use for that is you say that the conjugate base of methanoic acid is the most stable conjugate base of the 3. Okay? And we're going to talk about why. Why is it the most stable of the 3 as we look at some of the other ones here? Okay, but that's your basic understanding there is the stronger the acid, the weaker or more stable the conjugate base is. Okay, and the more stable it is, the less likely it is for that H plus to be able to reconnect back on there to reform the original acid that's in the molecular form. Okay, let's look at some more examples of this. In the following table, it can see that as the chlorine atoms replace the hydrogen atoms. So here, notice there's no chlorines. Here there's 1, here there's 2, and here there are 3. Okay, as that happens, okay, you notice that the pKa goes down. And as the pKa goes down, therefore the Ka value goes up. And again, we've got the stronger acid on the bottom. Here we have a lower Ka value, which means it is a weaker acid. Now, why does that happen? Why would trichloroethanoic acid be stronger than just regular ethanoic acid? Okay, this is due to the fact that chlorine is much more electronegative than hydrogen is. Okay, so because you've got really three very electronegative atoms around there, when that conjugate base is formed, it lowers, because those chlorines are so electronegative, basically it can attract those electrons closer to it, which, here's the important part right here, it lowers the electron density around that COO minus part. Remember, that hydrogen broke off. So it lowers the electron density, which means the electrons are more attracted to the chlorine side than they are to the COO minus side. And what that does is it pulls those electrons away from that side. So when the hydrogen tries to come back on to reform that acid, it can't. And again, what does that do? It increases the conjugate base's stability. Okay, so again, the conjugate base of trichloroethanoic acid is more stable than that of ethanoic acid. The stronger the acid, the weaker the conjugate base. Okay, the same can be said up here as well. Okay, this is the stronger acid, which means it has the weaker conjugate base here. Okay, and again, that makes it more stable than it would if you had all of those other carbon groups on it, like we do in propanoic acid. Okay, this next table shows virtually the same thing as that other table. Is that as you replace those, instead of a hydrogen, you put a bromine on there, and then a chlorine, and then a fluorine. Again, fluorine is more electronegative than chlorine is, and what bromine is, and certainly what hydrogen is. So again, what does that do? It makes all of the electrons more attracted to that fluorine portion. Just like up here, the electrons are more attracted to that chlorine side, which again, what does that do? It lowers the electron density around that COO minus. So you've got, like back up here, on this one, for example, you got CCl3 and then COO minus, okay? If the hydrogen's going to rejoin back on there, it's going to rejoin right there. But it needs an electron to do that. But the electrons, again, are so attracted to those chlorines because chlorine is so electronegative that it's less likely for that hydrogen to be able to rejoin there. And again, all you have to say is, it's the same thing down here, is that in fluoroethanoic acid, due to the high electronegativity of fluorine, there's a lower electron density in the COO minus region, which makes the conjugate base more stable than that of the other acids. Okay, and that's really all you need to know about that. It has to do with electron density, and it has to do with how stable that conjugate base is. The more stable the conjugate base, the less likely that hydrogen is going to be able to rejoin and create that molecular version of that acid again.